Okay, next topic is dispersion. And dispersion is essentially frequency dependence in the index of refraction. And that is epsilon r, mu r. And we saw, especially when we have conductivity, that epsilon does indeed depend on the frequency. So this is, let's say, n of omega. And what does this mean? Well, if you take the good old prism experiment, if you have white light, which goes into a prism, well then if the index of refraction is frequency dependent, then the different colors are going to get a different transmission angle here, right? So let's see, something like this. And then also here it's going to be give a, you have two refractions at both interfaces. Well, one at each, so it's two altogether, right? So if I take a white piece of paper here, then I will get out a spectrum here. Okay, so different index of refraction for different frequencies gives different colors here because of the different, they refract, or let's see, they refract at different angles. And this is because of the velocity v, right? Is equal to 1 over epsilon mu. And square root equals to omega over k. And if k is complex, then we just take the real part, because that's the propagating part. The other was a decaying exponential, right? But it doesn't affect the wave as such. So you get omega over real part of k. Okay, and this is called the phase velocity. This thing here, omega over k, is called the phase velocity. And it expresses that waves at different frequencies travel at different velocities because there's a frequency dependence on the epsilon here. Okay. And a consequence of dispersion is the following. If I have some localized signal, a radio signal, say, and I send it through a dispersive media, well then the different frequencies, well, let's see, this can be formed by a sum of plane waves, right? Like any signal. So if the plane waves travel at different frequencies, no, sorry, different velocities, then the localized blip is going to spread out. So you get something more like this after a while. So at t equals 0, when you send out the signal, this is what the signal looks like. And at t greater than 0, then the signal looks different because it spreads out. And I'm pretty sure that this is one of the biggest error sources in the GPS system because it goes through the ionosphere, which responds differently to different frequencies of radio signals. So if you have a localized signal in time from the satellite, it will spread out as it goes through the ionosphere. And we'll see this in a while, but the pulse here, let's say the center of the pulse, it doesn't move with the phase velocity. Rather, it moves with the group velocity, which I will denote by Vg. And Vg is equal to d omega dk. So to calculate it, I need the phase and the group velocity. I need the dispersion relation first. A typical example which you've seen before is water waves. If you have big water waves, so that the gravity is the source of the, let's say, well, the wave nature. You could also have small waves which are caused by the surface tension. But the big waves, you have that V is equal to 2 Vg. So when it looks like waves are coming towards you really fast, and then it sort of takes a bit longer than you expect, it's because the group velocity is actually slower. So you have, if you have a train of water waves, let's see, like this, then actually waves are going to appear at the end of the water traveling in this direction. Waves are going to appear here and then move forward toward the front of the packet and then disappear, while the sort of the center of the envelope function is moving at only half the speed. So let's see what this means in terms of electromagnetic waves. And one of the main reasons to look at signals composed of several frequencies is of course that a plane wave looks the same in all of time and all of space, so there's no information in it. I can't transmit information using a plane wave because well, it looks the same everywhere. There's a time oscillation and a space oscillation, but there's no change in it, so I can't really see if the guy sending the wave is trying to say help or send more food or money or whatever, because there's no change in it. So we need to superpose several plane waves at several frequencies to form a localized signal. To say, for example, well, when you get the signal, start the clock, for example. And we do that by superposing. Yeah. So to create some sort of localized signal, we superpose plane waves at different frequencies. In some frequency range, let's say delta omega over 2, say omega naught minus, and then omega is between omega naught minus delta omega over 2 and omega naught plus delta omega over 2. So I have some cutoff at both ends, because when you tune your radio, for example, you can't have plus infinity and minus infinity on the frequency knob. It would mean a lot of work. And the different radio stations would interfere, right? So we have to stay within some frequency range. Otherwise, we're going to make sure that we're the only radio station transmitting. Okay, and for simplicity, we're going to assume that we have the same amplitude for all the plane waves in this frequency range. So let's put up the math. So the E field traveling in the Z direction now. Of course, this is, as always, I just choose my coordinate system conveniently. So we have plane waves going in the Z direction. So it's omega naught minus delta omega over 2. So I just sum up plane waves traveling in direction Z at different frequencies. And they all look the same, of course. So E naught of omega. This is at given omega, how large amplitude does the plane wave at frequency omega contribute? And then there's e to I k z minus I omega t. Right. So this is clear, I hope. And as I said, we say that for simplicity, this is just a constant within this frequency window. So it's just E naught. And then omega naught minus delta omega over 2. Omega naught plus delta omega over 2. And the plane wave. Like this. And this part here now is essentially the Fourier transform of a square pulse. Because it's 0 everywhere except at some interval where you have a constant contribution. Okay? So saying that I emit a bunch of waves at different frequencies within some window at the same amplitude, which is hard, so this is normally something softer, but let's say I can do that. What does the time-dependent field look like? And then I need to perform the integral, of course. So let's see if I can do that. And now note that k is a function of omega, right? Because it's a dispersive medium that we're interested in. Because if this was in a vacuum, well, we could just do this and there would be no dispersion and the signal will keep its shape all the way from the transmitter to the receiver. Okay, but now because we have a finite and not very large frequency window, so we assume, let's see, the width of the frequency window is small compared to the frequency, which means that I'm just changing the frequency just a bit, not too much. Then I can Taylor expand the dispersion relation because it doesn't depend, well, at least for now, let's assume that it doesn't depend very strongly on the frequency. If it depends strongly on the frequency, then I'm most likely stuck because it's going to be hard to get the signal across. But if it doesn't depend too much on the frequency, then I can say that k of omega is k of omega naught plus dk d omega at omega naught times omega minus omega naught plus higher order terms. This is essentially a first order Taylor expansion, right? So and this looks like one of the group velocity, and indeed it is. So let's see. So now I can, well, if I keep all the terms, this is exact, but I'm only going to keep the first two terms, of course. So it's approximately equal to k naught, which is k at omega naught. Seems logical, I hope. Plus omega minus omega naught over Vg. Okay? So d omega dk is Vg, so it's 1 over Vg. And then there's the difference from the central frequency. It's a linearized dispersion relation. Just to remind you. Okay, and now the phase in the integral. I'm just going to do that here. That is the ik set minus I omega t. If I insert the dispersion relation into that, I get that, let's see, k set minus omega t is approximately k naught set, that's this term, then minus omega naught t. No, wait. Omega minus omega naught over Vg set. And, okay, I need some more space. Let's keep this for now. Okay, so k set omega t is equal to the k0 set plus omega minus omega naught over Vg times set this should be approximate, and omega naught t, because I can write omega as omega minus omega naught plus omega naught. This is trivial, right? Because I add and subtract the same constant. So I get this term, and then omega minus omega naught t. Okay, this seems like a lot of hassle, right? But what I'm trying to do is, of course, to get an integral in terms of this variable here rather than omega. Okay? So if I can do that without messing things up, you have k naught set minus omega naught t. So this looks like the ordinary plane wave at the central frequency. And we have the omega minus omega naught. The frequency dependence is stuck here, set over Vg minus t. There we go. So this is frequency independent, meaning I can take one of those exponentials and put it outside. And I will show you how that is done. So we had that E of set t, our superposition of plane waves, is equal to E naught, then e to the power of something frequency independent. So I factor that out of the integral. And then there's an integral of omega naught minus delta omega half. The plus, the same thing. And now I'm stuck with the difference here. Okay, so it's e to I omega minus omega naught. And r set. All right, so now I can change variables, I hope. So I'm going to call this large omega. And I'm just going to define this as t, because this now is frequency independent, so no, it's not. Yeah, I'm assuming a linear form of the dispersion relation around the central frequency, meaning that the d omega dk, which is the group velocity, is indeed constant. Okay, so this is frequency independent to first order in the dispersion relation. And now I should be able to solve the integral, which is simply minus delta omega halves to plus delta omega half d large omega e to I omega t. And this is a very simple integral, of course. So it's 1 over it. And then e to I omega t from omega half to minus omega half. Or perhaps vice versa. Anyway, solution is pretty simple. This is e to plus something, e to minus something, and that's a sine function essentially. And this I is also in the sine function, if you remember that. So we get something that is equal to, so I is equal to 2 over t sine delta omega t half. Okay, and I can rewrite this to, let's see, delta omega sinc delta omega t half. And what is sinc? Now, sinc of x is simply sine of x divided by x. Okay, sometimes it's defined with a pi here. So there might be some pi, I don't know, here, wherever. But that's not the definition we're going to use. Just to warn you that this function can be normalized in several different ways. Okay, so now what does sinc look like? So I'm going to sketch what that function looks like so we know what we're dealing with. So, sinc of x, which is sine of x over x, it looks like the following. There's some peak here at 1. If you take the L'Hopital's rule, it's easy to see that that's the limit value as x goes to 0, and you get something that looks like this. It's some function that it's peaked at the origin and is oscillating as you move away from the origin, and decaying, of course, because of the 1 over x dependence. All right, and the maximum amplitude is, as I said, at x equals 0, because as you move further out, then 1 over x starts to decrease the function. Okay, and the maximum amplitude was at x equals 0, but here x is delta omega times t divided by 2. So this is what is in the sink here. So when this factor here is equal to 0, then we have the peak of our pulse. Okay, so let's see that the frequency is a constant, 2 is a constant, so take those out. T equals to 0. T was equal to z over Vg minus t is equal to 0. And we get that z, which is now the position of the peak, is simply equal to Vg times t. Okay, so we see that the peak of the pulse is indeed traveling at the group velocity, right? So that's pretty typical. The peak of the let's see. So we have an exponential variation here, which is fast, and then a sine here, which is slower, because you have delta omega here and omega here. So this oscillates a lot slower because delta omega was much less than omega 0. What was I trying to say? Yeah. So it's a signal looking like this that's traveling through space and time. Okay. Yeah, and the energy density of a wave is proportional to E squared, right? So this is E as a function of time and space. And because U is proportional to E squared, well then the peak here is where we have the most energy. So it seems fair to assert that energy flows at the group velocity because the peak flows at the group velocity. Okay, so now let's try to analyze a bit mathematically the wave package which we've created from equally weighted frequencies, so plane waves. And then first of all, we're going to look at the picture as t equal to 0 to see what happens then. And then we're going to look at it at z equals to 0 and see the time dependence. So you see the spatial and time dependence separately. Okay, so at t equal to 0, to see what does the instantaneous picture look like then we have that delta omega t over 2, which is the argument of the sinc function, is equal to delta omega over 2 z over Vg, which we can also write as z over 2 delta k. Because, let's see, delta omega over Vg is equal to delta k. Now I use that, the derivative of the dispersion relation is constant across my frequency range. Okay, and then I'm looking at the real part of my signal. So let's see, real part of E at t equals 0, well then we had the exponential in front, so the real part of that is just a cosine. K naught set, time dependence is gone, and then the integral gives a sinc, so it's sinc, there should be an equal sign, sinc of set delta k over 2 and E naught delta omega. All right, so let's see. Yeah, as I said, this now is a slow oscillation because delta k is small. Compared to the center wave number. And this is a fast oscillation. This basically then forms an envelope for the fast oscillating function. So what we get is something like this. Oh, I want some more space. Okay, so what we have is the following. Real part of E at set time equals 0 as a function of the position along the propagation direction. Then we have the envelope, which is some sort of decaying sine function, like this. And if I mirror it, it's going to look something like this. Okay, and inside it I have a fast oscillation. So I have this envelope is the sinc. And the stuff going on inside the envelope is the cosine. Okay? And let's see, the first 0 of the sinc function is of course when the numerator is 0. So sinc of x is sine x over x equal to 0. Well then x is equal to pi halves. And I'll need that to pi? Yeah. Sorry, pi. Yeah. Of course. Anyway, the half isn't all that important anyway, because what I'm trying to estimate is the width of this pulse. And I'm just going to use this first 0 as an estimate of that. So I say set 1. That's the first 0 at the argument of the sinc equal to pi. And that is set delta k over 2. So let's see. Set 1 delta k over 2 equal to pi. And then set 1 equal to 2 pi over delta k. And now I can use set 1 as a measure of the pulse width, as I said, because if the let's see, if delta k is small, then the pulse gets wider, right? And then the zeros move out. So I use delta set approximately set 1. And that is just 2 pi over k. All right. And what this means, delta z is a function of delta k. What you get is, in the end, is that delta z times delta k, so the width of the pulse, times the width of the frequencies, I mean how many frequencies are put in, is roughly equal to 2 pi. And this is what we call the classical uncertainty relation. And it says that if I want a localized pulse, then I need a lot of frequencies. I need a large delta k. And if I want to use only a few frequencies, well then I'm just going to have to accept that I'm going to get a large pulse in space. Or wave numbers here to be precise, but this is depends on omega, right? Okay. And yeah. And if we look at the time dependence at z equal to 0 to well, to complete the picture, now we looked at the space dependence at a given instant of time. Now we look at the time dependence at a given position in space. So let's see, z equals 0, 0. And then we get that delta omega t over 2 equals to minus delta omega t over 2. This was the t is z over vg minus t, right? So so the z is equal to 0, meaning we only get the time here. This is the same. So you get that r real part of e of 0 time is equal to something that's similar to the spatial case number 1. So you get E naught delta omega sinc delta omega 2 over t over 2 cosine omega naught t. And this is a fast oscillation because omega naught is large. And this is slow because delta omega is small. It's completely analogous to before. And then if you look at the first 0 to get the width of the pulse, then you also get, in this case, a connection between the frequencies you put in and the size of the pulse, which is just that T1 is equal to delta. Let's see. No. Yeah, T1 is 2 pi over delta omega, like Z1 was 2 pi over delta k. And we arrive at the uncertainty relation between frequencies and time, which is simply delta omega times delta t is approximately 2 pi. Like this. Okay, so the shorter the pulse you want in time, the more frequencies you need to put in. And this is basically the idea of, again, the GPS system, that you send out some signal and you find out at what time does the signal reach you. And if you know what the time is, if you have a precise watch yourself, then you can see the time difference from different satellites. And if you then know the positions of those satellites, then you can determine your own position. And then you need to find out at what time does this signal arrive. And what our equation is saying is that if you want to know where you are, well, then you better know, then you better have a lot of frequencies. Otherwise, you're just going to have a wide pulse, and the uncertainty is going to be very large. So, any questions on dispersion and absorption? Nothing? Have you seen this in another course except quantum mechanics? No? Okay. Yep.
I learned that if you have group velocities greater than the speed of light,
I haven't seen that, but I think it doesn't really matter if the group velocity is larger than the speed of light, because it's the if you have some signal. I mean, at some point in time there is no signal. Before you built your, let's say, signal transmitting device, there was no signal. So you have a signal that looks like this. If you have t, then it starts at some point. Well, the other way around, I guess. Then it starts. So what's important is the front of the signal. Yeah. So the signal can change shape, in fact, while it's traveling through some material because of dispersion. But it's it turns out to be not important, but that's a pretty special case. So I wouldn't worry too much about it unless you have some really interesting medium to travel that your light or electromagnetic waves are traveling through. So, but I think in general you're right. But I think I heard that there's actually something like 7, 8 different velocities you can define from a wave, like the front and the rear velocity and the center and group and phase velocities. So you have to take care. We'll actually see next Monday. We'll see an example of the phase velocity being greater than the speed of light. Okay, so you have something to look forward to. Anything else? Okay, and then now we're moving on to something completely different, which is called guided waves. I think we'll just get briefly started, but I'll introduce you to the idea so you can think about it in the weekend. And the idea is more or less as follows. If we consider the following system, we have air, glass, or in principle some other dielectric medium, and then metal here. Then you know that because of conductivity, any wave traveling in this system is going to be attenuated in the metal. And we also know that for certain wave numbers, k parallel wave numbers, so if this is k, this is k parallel. For certain k parallel, the wave is also going to be evanescent in air. So if I draw the dispersion diagram, k parallel on the abscissa and omega on the ordinate. Then you have the light line in air. And the light line will simply where k parallel is equal to omega over c. Meaning that all of the, let's see, the k parallel is along the interface. All of k vector is along the interface, meaning that the wave is traveling along the interface, so I still have a wave. While if I go on the right-hand side here, k parallel is longer than, let's see, k parallel is greater than omega over c in this region. So we have evanescent waves. For glass, the dielectric constant is different. So the velocity of the wave is different here. So this is light line for glass. This is what we talked about before. And then in region 1, here, then you can have guided waves, which is essentially total internal reflection. The light is sort of bouncing up and down. That's the geometric picture, which is far from complete, but it gives you the idea. Okay? So because of Snell's law, say, I can't have waves in air in this region, but I can have waves in glass. And yeah, so the field is evanescent in the air and in the metal, but not in the glass in this region 1. And yeah, in this part here of the space, then the waves are confined to the glass because they can't move into the metal and they can't move into the air. So they're called guided waves. And this is the principle used in waveguides in, for example, radio frequency machinery and optical fibers, for example. That's this principle. And I want to tell you before we start that there's not, you don't have the case, let's see, yeah. In this region, only certain combinations of omega and k parallel are going to allow traveling waves, okay? So I don't fill all of this space by modes, but only some combinations of k parallel and omega are going to be allowed, okay? So not all combinations sketched here are possible, but if there are allowed combinations of k parallel omega which give propagating waves, they're going to be in this region 1 here, okay? And another example of a waveguide is, of course, an optical fiber. And I'm sure you all seen a waveguide which is large. So if I have some cylinders, say, I'm sure you all played around with this in high school, perhaps. You shine some laser at some angle, and then the light just bounces inside. You can see the waves going through the glass or plastic. But for this to happen, d has to be much larger than lambda. So what we're going to take an interest in is, of course, when d is more comparable to lambda, because then the geometric optics completely fail, because you can't have waves that are bouncing if there is no room to bounce, so to speak. So we're going to look at well, yeah, cases where you have that the dimensions of the waveguide is comparable to the wavelength. And in fact, it can be even smaller than the wavelength in some optical fibers. And one way to build an optical fiber is the following. So let's see. If I have a core that has one index of refraction n1, and then I put something outside with the index of refraction n2, and then this is also contained in some other material with n3. So let's say it's a cylinder. Let's say that lambda is on the same order of magnitude as the components of the fiber. Then it can actually be convenient to have n1 less than n2 and n2 larger than n3. Because this actually allows something called transverse electric and transverse magnetic waves at the same time. And well, or they're called transverse electric and magnetic. And there are many other structures that will also give you guided waves, such as well, you have a thin film of glass on a metal, but it could also have some thin film on a glass which has a higher index of refraction. This is the system we examine in one of the labs in the advanced optics course, which I'm teaching next spring. Then we examine what modes do you have in this, let's say it's glass. And then there's a thin film, which is, I don't know, it's on the order of microns. So it's a bit longer than the wavelength, perhaps. And then you get only some modes through this film. And well, next Monday we're going to go through the theory for how you calculate what modes do you get, how do they propagate, and so on. So I will see you on Monday. If you have any more questions on this, I guess they will be answered then.